Hey everybody, it's Ripley again. We are in chapter 10, man. We're on the home stretch. And these last two chapters are going to be pretty straightforward. There's not going to be a whole lot to them. Chapter 10 in particular is going to be done predominantly on your calculator. There's not going to be a whole lot of lecture to it. I'm just going to show you in class how to plug stuff in. But I do want to give you sort of the foundation for everything, okay? This chapter is about correlation, all right? Correlation is real simple to get your brain around. What it is it's the strength of a linear relationship between two related variables, and these are x, y. Okay? So sometimes you'll hear this term referred to as bivariate data. And let's get you a little bit of background here before we get crazy. Let's say, I mean, there's lots of ways to think about this, but let's just come up with a quick little example to describe it. Let's say that we take I want to know the relationship between SAT English, or SAT Mathematics and SAT, what's the other one? I think it's English score, right? Or verbal score, right? So you got a verbal and you got a math score. So what we do is, let's say we take 20 people, and all that we're going to do is I want to figure out if the verbal score affects the mathematics score. So I don't know what you remember about this from your function, but what you've got is an independent variable and you've got a dependent variable, right? So I mean, really what we're doing here is we're just doing a bunch of x sub n and y sub n's. And in this case, this is going to be our verbal and this is going to be our math. Okay? So I would just go up to 20 people and I'd say, hey, what'd you get on your verbal? And they'd be like, oh, I got a 650. Okay, what'd you get on your math? Oh, I got a 720. And that would be our first, this guy right here would be, think of this almost as our first data value. And then I'd go up to somebody else, what'd you get on your verbal? Oh, I got a 420. What'd you get on your math? I aced that, I'm awesome at math. Okay, you see what we're doing? So, and I would end up with 20 values, because n is the number of ordered pairs. Now, don't think of ordered pairs so much like you do with when you're talking about geometry or you're talking about functional theory. All right, what we're doing is we're talking about a relationship between an independent and a dependent variable. And then what we do is, just like always, we graph them. Now, think about this. You could have, if I plot all of these points on a graph, and I end up with something. Let's say that they're 20 like this. I got a couple crazy ones. And I end up with that. Now, does there appear to be a strong linear relationship between, so these, what did I say? These are my verbal scores, and these are my math scores. Well, now, there's certainly not as strong a linear relationship as if I did this and this, right? This would be a perfect linear relationship, right? Or something like this. If I had a point here and a point here, whoops, and a point here and a point here, I think that's perfectly linear, yeah, then that would have a perfect linear relationship. But this guy right here is just approximately linear. All right, there certainly appears to be a linear relationship between the x and the y variables. All right, but what we need is something that measures the strength of that linear relationship. How about this? What if I did something like this? Let's go back to black. Let's say that I had a bunch of points that looked like this. Well, think about it. If I tried to draw a line through this that was supposed to be representative of the data, would it be that one? Would it be that one? Would it be that one? Or that one, you know what I'm saying? This one's pretty easy to tell. I could actually just kind of draw a line. You know, that's supposed to be, we could call that, I suppose, a trend line. We'll get more technical with what we call it here in just a little bit. All right? So this has a relatively strong linear relationship. This, on the other hand, has nothing. Now, couldn't we also have data that did something like this? You see that? Now, your spidey sense may be tingling. And you maybe say, well, okay, it doesn't have a linear relationship because I would either want to draw a line this way or I'd want to draw a line this way. And if I wanted to trend through all of the data, I'd probably end up with a line that looked like this. And that line is not representative of any of the data. So this has what's called a curvilinear relationship. Curvilinear relationship. Now, correlation, for what we're talking about, correlation has nothing to do with curvilinear. All right? I think there's two L's in curvilinear, by the way. We are only measuring the strength of the linear relationship between the two data, between the independent and the dependent variable. All right? Now, there's a way to measure that. Of course there is. Otherwise, we wouldn't be talking about it, right? And that's called Pearson's coefficient. So the Pearson's correlation coefficient. And we're going to keep this simple. If you look in chapter 10.2 and you look at the formula to come up with Pearson's correlation coefficient, which is known as R, the formula is god-awful. It's horrendous, and it's completely unnecessary for what we're doing. To be honest with you, I think I've had to do Pearson's correlation coefficient one time by hand, and I wanted to poke my eyes out for having done it. Excuse me, I gotta get a drink. All right, but Pearson's correlation coefficient is the measure of linear. It's the measure of the strength of the linear. Just linear for now, okay? You'll get into more heavy topics down the road in your future statistics courses, but for now, just think of it as the linear relationship between variables, between independent, which is the x, and dependent. Sometimes you'll hear these referred to as predictor variables, dependent, which is the y variables. Okay? Now, like I said, everything that we do in here is going to be done on the calculator, and we're going to do it in class. So don't freak out, okay? I promise we're not going to have to do any of these by hand because they're absolutely horrific. All right, you ready? R always lives between -1 and 1. Always. Now, let me give you an example. Back here, the strength of the linear coefficient for this set of values would be approximately 0 because there wasn't anything. In this case, R would be a perfect 1. In other words, there is a line that passes through all of the points. Now, there's a bit of confusion here that you have to try to avoid. Notice maybe a little bit, I don't know, I didn't mean to obfuscate anything here, but this may be a little confusing because the slope of this line is also 1, all right? But R doesn't have anything to do with the slope except that they always share the same sign. I'll show you. For this guy, R equals -1. It's a perfect linear relationship. However, it's going in the negative direction. Do you remember, you've probably seen this before, where you talk about negative relationships versus positive relationships. Excuse me. In statistics, that's really what we're measuring here. All right? Now, this guy over here, I don't know if I had to guess, and we're not actually going to go through it. Like I said, we're going to do all of this in class with our calculators because it's so much easier. I would guess that the strength of the linear relationship on this would be probably about maybe positive 0.9. All right? So let's go back over here, and we are definitely going to say that this is not a slope.